university that will happen the Dynamics Days this year, Dynamics Days Latin America in Curitiba. So if you have any questions, and my supervisor is Professor Thiago de Lima Prado. I know he will be on one of the organizations. And this work is a joint collaboration with Professor Peng Ji from Fudan University. And we talk about signal propagation spiking networks. The motivation is quite simple. We want to understand the brain, so we need to understand the brain that operates using spikes. It's important to have some framework on that, and also to design better machine learning, because despite the brain doing very complicated cognitive tasks, it is energy efficient and it's low frequency. Like a spike happens in maybe a maximum kilohertz, but some CPU on your computer works on gigahertz. And how does the brain is able to do this computation using this energy efficient and low scale dynamics? Okay, but there's a problem because spike generation is highly nonlinear, and the brain or any interesting complex system works on an open system, like a living organism. So if we simplify to something like the equilibrium, it doesn't make sense. So we want to accommodate no-equilibrium dynamics as well. And to exemplify, nowadays we have this very modern experiment that's called pump probe. And this paper specifically is analyzed the C. elegans brain. So they put the worm here, and they are able to map all of the neurons, the 302 neurons in the brain. They can observe it using calcium imaging, and they can also stimulate any neuron in the brain using 2-photon or optogenetic stimulation. And this is the kind of data they have. So they can scan, they can have a time series for all of the neurons in the C. elegans brain, and they stimulate single targets. And they can stimulate several times the same neuron, and every time they stimulate a neuron, they can call it a trial, and they analyze the signal propagation or the response to all the other neurons in the network. But when you have this kind of data, they are interested in a living organism, so this is complicated. For instance, if they stimulated this neuron here, the response of the stimulated neuron is quite consistent, but the responding neuron doesn't have a consistent response. So sometimes it's responsive, and on other times it's not responsive. And it's with a linear theory, this is quite difficult to explain. This is a nonlinear phenomena in an open system. So there are several sources of noise, of fluctuations that can affect this phenomena. But yet, the C. elegans is able to perform cognitive functions. That is, it can seek, like, if it is stimulated in some way, it can go to some direction, and it's still a behaving animal with reliable functioning. So how can I understand that? Even though the neuron response here is not reliable, like the microscopic response is not reliable. Okay, and now I'll go to a very simple model, or simple toy model, that is, think about two neurons, a source and a response, and you are interested only on the spike types. And when you measure it, you have events that may be correlated. So you do not assume a model, you just observe it. There is this paper here that defines this kind of network that's called an event space. That is, you can have these spikes. You can assume it, actually, that these spikes are causally related through this well-behaved function that they consider a smooth function. Just like this, it's a smooth manifold. In a way, you can derive it. What they could do with these results is to make the backward engineering. So with the spikes, they can reconstruct the network. And it's quite simple. It's because when you have an excitatory connection, and there is a spike on a specific neuron J. This spike will make the interspike of the postsynaptic neuron shorter. And if this is an inhibitory connection, the interspike interval will be longer. And this is very simple, and this is already able to reconstruct the network only from these timing patterns of the network. All right, but they did that. They didn't assume a specific model for this function, just this causal relation. And they call it functional connectivity. However, when we want to explain it better, we need to assume some model to get that some physical interpretation, have some parameters, we put some variables that can be, for instance, the membrane potentials. So if you want to use a physical model, you can use like the Hodgkin-Huxley model that will model the capacitance and the membrane potentials, but it's usually these physical models are pairwise. Nowadays we have like the hypergraphs that can explain something that is not related just to pairwise connections, but usually it's a pairwise connection. And how we can go from this pairwise description, deterministic description, to a functional description that could be macroscopic description. This is our focus, how we can do that in a spiking model. All right, so let's take a very simple model for a neuron, a spiking neuron that is the leak integrating fire model. So this is just a capacitor with a leakage, and the connection uses a kick. So every time a presynaptic neuron spikes, we add a constant here that comes from the adjacency matrix of the network. We can have some tricks, and in between a spike, we can integrate the system because this is linear, and then the integral of this delta function is just this constant, but because of our trick, appears exponential here. However, this model still has this microscopic variable that's the membrane potential. It's not in spike times. Then we can do another trick that's actually approximation. That is, because we integrate in between spikes, the membrane potential here and the membrane potential here is known, at least for this model. That is, this is the reset or the equilibrium value, and this is the threshold. So we can put it, and the threshold and the equilibrium value are actually parameters from the model. So now the membrane potential is not a variable, but the variable now in this equation are the spike times. And then this equation, it's a function based on a model for that generic phi that I showed before for that PR paper. This has some causal implications. That is, if you have this interspike interval, the spikes that matter for this spike, IM here, are in this window. But then if you go to a second neighbor, the causal spikes go further to the past. And this is what we want to explain. Okay, but is this equation right? What I did here to prove is that remove this neuron J and consider this spike comes from a Poisson distribution, that is like noise. And that's what I am showing here. And then we couple it using that model for the leak integrating fire model that I showed. And the curve is like this. For some specific connection weight, we have the theory. And for different Poisson rates, for this noise, we can have different interspike interval for the post-synaptic neuron. And these are the variables, and when we sum it, this is somehow an order parameter that is related to the input current the presynaptic neuron is sending to the postsynaptic neuron. Okay, but that is still like an analytical solution for the leak integrating fire model that's still pairwise, like I show here on the left. What we want is to write the state or the spikes of this neuron I as a function of any other neuron in the network. Let's say a second neuron. With this equation, it's quite simple. We just we have the solution for this, each of these tjk, and then we just input here. And then the equation is still quite the same, but now it's not the adjacency matrix. We have something related to the paths we can take from one neuron to the other in the network. Okay, and again, does this equation works? We show that yes, this works. Because the source is still a single neuron, we can make this as a one-dimensional source, that is this order parameter. And then the first neighbor, just like I showed, this is for a specific firing rate for the source, that is the first neuron. And then for the second neuron. And the approximation we did is not perfect. I show here, we can miss some, but it's quite good, even for the second neighbor. We can, so if we know the input spikes, we can predict the output spikes. Here, it's for the simple chain. And just to finish, I don't know how many time I have. Okay, so we can apply it for a more complicated scenario, that is, if we have a network, but now the input, it's not one-dimensional here, so it's interesting to make some decomposition of the network. Here, we use the singular value decomposition that's related to how we can encode and decode the patterns the network generates. Okay, and this is a simple MNIST dataset classification. Oh, sorry, no, not MNIST. This is wrong, sorry. This is, we put some, this is the source, so it's a reservoir of spikes, and then we input some patterns here. And just using SDTP, winner takes all rules, we can train the network. And then this is the singular values evolution of this network as it learns these patterns. And the output just learns that it can display these two patterns. And when the network learns these two patterns, two of the singular values gets more higher. Okay, but how does this effective propagator works? What we can do, we can take the singular value decomposition and then multiply these singular vectors, the decoding and encoding, and then another decoding singular value, singular vector, multiplied by the singular values, and get some effective singular value. So that is for any pair of neuron in the network, we can estimate how activity patterns can propagate from any neuron L to a neuron I in the network. And this is the last figure, that is, we can have the curves for the usual singular values and for the effective singular values. And we show that as the network uses SDTP rules to learn the stimulation, to learn the output patterns, the singular values increase. So, and then while it is accommodating this learning, these output patterns, they have this behavior here that we cannot explain. We are trying to analyze it, why it decreases afterwards. Okay, and that is it. Thank you very much for your attention.
Okay, thanks, Gabriel, for your presentation. I have time for some questions. Okay, so I have one. In those experiments regarding the neuron activation of the C. elegans, it's possible to separate what is considered the rest state of from the neutron that you are stimulating. For example, I believe that the species it's alive.
Yeah.
So it performs some kind of biological functions, and these will trigger some neural stimulations regarding of you.
Yeah, one of the problems is that for this experiment, the worm has a short lifespan, so they need to make all these stimulations in like maybe 2 hours experiment. So they do this, and they cannot wait like for infinite time for the system to relax. So they apply stimulation, and after 1 minute, they apply another stimulation to another neuron in the network. So, okay, they wait sometimes for the system to relax, but it's never without any fluctuations. There's always some fluctuations.
Okay, thanks. More questions? So let's thank the speaker again.
Thank you.
Now we're going to have in Maria Vithória, which will talk about the influence of topological characteristics on the dynamics of neuronal networks. Oh.
I've changed it a little bit.
Okay. Although, esqueci o nome. Okay.
Hi everyone, my name is Maria Vithória, and I will present a short presentation of my master's work, which is in neuronal network dynamics with Professor Gonzalo Travieso and Thomas Peron at the University of São Paulo in the Physics Institute of Physics. So this is the agenda of my presentation. And to study neurons in the brain, usually you use neuronal models. A very famous firing rate network model is described by Sampolinsky, Crescent, Summers. Oh. Esse não funciona? Oh. Ah, ok. Thank you. Okay, nice. So I'm studying the model described by Sampolinsky, Crescent, Summers, a firing rate model. And in their work, they describe the transition from a stable activity in a neuronal network to a chaos regime. I studied this, but with excitatory and inhibitory neurons, and through numerical simulations. So this is the paper this is their paper, and the model is described by this differential equation. Here we have this minus x, that it's a natural decay. We have the sum of the neurons input through and this gain function, which is equal to hyperbolic tangent. So this model is a nonlinear model. This is the vector form of the differential equation, and the elements at the W matrix are drawn by a normal distribution with mean zero and variance equal to sigma square over n. And this is important because they have a result involving this that I will talk about. And the initial conditions is drawn by a uniform distribution. So the main results were that this parameter related to the variance of the synaptic matrix. When this is lower than 1, we have a stable fixed point. We will see something like this. All the activity of the neurons going to 0 or converging to some value. With sigma higher than 1, we have a chaotic regime described in the paper. And we will see like a more unstable behavior, like this. The sigma equal to 1, we have a transition between both regimes. And again, I will study this with inhibitory and excitatory neurons. Some researchers have studied this, and they show that we can have like a balanced equation when we have the excitatory and inhibitory neurons, and so the sigma A will be different for sigma I, because we can have a different portions of the neurons in the matrix. We can see the behavior with more excitatory neurons and less inhibitory neurons, and so on. In the numerical simulations I've been doing, I use the model that I said, and these parameters here. So I am analyzing this sigma parameter from 0.6 to 2.2. And with not so much resolution yet, because I'm already exploring. And I am studying also the finite size of the networks, because in the work that I show, it's an analytical work. So they use n, the number of the neurons of the network, approaching to infinity. I am studying this with finite size, like with 100, 200, 500, and 1,000. And I will evaluate with the maximum Lyapunov exponents to observe the transition to chaos. So the maximum Lyapunov exponent, if it is lower than 0, we have a stable behavior. If it's higher than 0, positive, we see a chaotic behavior. And near to 0, we see like a transition. So this is some graphics that I did. Here we have the network with 100 neurons, and I am analyzing with 80 excitatory neurons. So this shows that with the sigma equal to 0.8, we have the neuroactivity converging to 0, which shows stable regime. As we increase the sigma parameter, we see that different behavior in this activity. Equal to 1 is still stable because it is converging to some values, but as we increase more, we see that some of the lines doesn't converge. And this is matches with the theoretical results from the paper. Here we have the n equal to to 1,000. So higher. No? And we see the same behavior, but we observe that there's the unstable behavior. It occurs before the end when we have it with n equal to 100. And studying the finite size effects, we can see here a graphic of the maximum Lyapunov exponents in sigma. And here, each line, it's for number of neurons. So the blue one, it's with 100 neurons. And in this graphic, it's with 20% of excitatory neurons, and the rest of them inhibitory. We can see that in the blue line, the Lyapunov exponents are all negative. They doesn't cross 0. But the red line, we can see crossing at here in sigma 1.4. So, and the others, like orange, it crosses in 1.9. So we observed that increasing the number of the neurons in this network, we can see that it goes to chaos in lower sigma values. So here it's 1.4, and in the analytical results, the transition occurs in sigma equal to 1. We don't have this here, but we think that increasing the number of neurons in a matrix, we will be more near for the analytical results. And we also observe discontinuous here in the one that we are trying to make sense yet. So these are the next steps, evaluating the finite size with more networks with different numbers of neurons, and investigate the critical threshold for the transition to chaos. And we want to study topological characteristics and how these affect the network dynamics in this model, like assortativity, modularity, heterogeneity. So this is the references, and thank you very much.
Thanks, Maria, for this nice presentation. We have time for some questions.
Congratulations for your talk.
Thanks.
It was not clear to me what kind of underlying network you use to determine the weights. Okay, the weights are words distributed between -1 and +1, but the networks is a complete graph. Everyone is connected to everyone.
Yes, in these results, everyone is connected to everyone. It's a dense matrix. And in future experiments, we will do with sparse matrix.
So that's my question. Do you expect big difference when you include a sparse matrix, a dense matrix?
I expect, but I don't know what I will see in it. Maybe like more unstable behavior because we will be more near from biological descriptions.
And about real data, could you try your modeling using some data sets? There is many biological data that are available to investigation. Have you thought about this?
We didn't use it yet. We still using the synthetic matrix, but it's a plan using real data. Thank you. Nice. But if I use the data, I will not like using the blue matrix that is described in the paper, right? Yeah, it's because my objective is reproduce the analytical results with numerical simulations. My first objective. But yeah, I think it will be better to do it with data.
Do you have any interpretation from the biological point of view of what the different regimes of the Lyapunov exponent would mean? I mean, what means a chaotic brain, what it means a more stable brain, what would be happening in the actual brain, like in a physiological point of view, you know, that, how to explain that?
People are not clear yet about it, but they relate it to like a disease, Alzheimer and epilepsy. Yeah.
So let's thank the speaker again. And now for the last talk of the day, we will have Leonardo Rodrigues, which will talk about motif synchronization for characterizing epilepsy.
Are we using this microphone or this one?
Yeah, this one. Your presentation is here.
Yes.
Okay.
Out time.
Oh, perfect. Okay.
So this works the slides, and this is for the laser pointer. Okay, I'm gonna have a hard time with these two. Hello everyone, my name is Leonardo. I finished my PhD last year at Unicamp. So this is some of the results I had for my PhD, which I'm still trying to publish, and some things going forward. So my advisor was Professora Gabriela Castellano, and I also did a sandwich internship at Newcastle University in the UK. So I work with epilepsy, just as the last speaker was mentioning. Epilepsy is a disease that affects around 65 million people in the world. About 2/3 of these people respond well to drugs. 1/3 doesn't respond very well to drugs. And of these 1/3, oops, sorry, how do I go back? Okay, the smaller one. Of these 1/3 that doesn't respond very well to surgery, 20% can go to resection surgery, which is to try and find where the focus of epilepsy is in the brain and try and remove it with surgery. And about 80% don't have an optimal treatment. They don't have an alternative, any viable alternative, and have to live with this condition. And even in the cases where surgery works, the success rate is about 60%, meaning only about 60% of the people that go through surgery become seizure-free. So EEG analysis is very important for this resection surgery and epilepsy in general, which is this cap with the electrodes. I think you're familiar with this, that produces these squiggly lines, which is the EEG signal. So visual inspection of these squiggly lines is very important for clinical evaluation. Clinicians look for, I don't know if you can see this, but there's a big spike here in red. This is interdictal epileptiform discharge that happens quite often in the signal, even when a person is not having seizures. And also, because seizures are not very frequent and you can't expect a person to come in having a seizure every time, seizures are these highly synchronous events that are rare to occur. You look for these small spikes here, the interdictal discharges. And connectivity analysis on the EEG is, there are many, many publications that work with this, is you try to make a connectivity matrix, try to see how different channels speak with each other on your signal. And you do a time series for this. So you have a sweeping window that goes through various connectivity matrices, and you see how these networks properties change throughout your signal, and you can associate that with, well, you can try to use that to characterize epilepsy. So on that note, I work with a nonlinear connectivity technique, which is called motif synchronization. It is nonlinear because instead of looking at amplitude, we look at patterns or amplitude patterns. So you have your time series, that's this, and you break down it into sequences of 3 points, and you see if these sequences, like 3 points going down, or 3 points going up, or 3 points going down, or something in the middle. So for 3 points, you're going to have 6 possible permutations, and you transform the whole time series that was coded into voltage, amplitude, into a series of these symbols, right? And the way we measure connectivity is to look at the sequences of symbols from 2 different time series at a moving time window. So we want to see if a sequence here is going to repeat itself on the other signal with some delay, right? These are also called motifs, symbols, or ordinal patterns. So we can make something like this. This is a time-varying graph that sweeps through our whole EEG signal. And then it's going to have these frames. If we sum and normalize these frames over time, something quite nice we found out happens for the patients we analyzed. So we analyzed 75 patients from our epilepsy data set at Unicamp, which is, you're going to have more connections happening on the areas that are connected to the focus or related to the focus of epilepsy in the brain. This is quite nice, even considering you have a low spatial resolution type of analysis, because EEG signals, they have a lot of smearing because they go through scalp and various types of attenuation. So if we look at the individual frames of our time-varying graph, these are well correlated with events on the EEG. So this is the EEG time series, and these lines here are 2 types of marked events. So here is a spike. I don't know if you can see, but here the lower lines are electrodes on the right hemisphere, and the upper lines are electrodes on the left hemisphere. So this was an event that was marked by clinician, and there's a connectivity pattern associated with it. I didn't go into our threshold or anything like that. And these graphs, because of our thresholding, they're usually very sparse. But whenever there's a marked event, you can have an increasing number of connections here. So this is for a patient that had events on the both right and left sides. If we only look at events on the separate sides, you can see that it's very clearly marked for the patterns we have. This is considering the labels the clinicians put. And this all events on the right, events on the left, and the whole time series. So even when we look at the whole time series, you see there's more connection weights here and here, which are the areas where this patient had a epileptic focus. This is quite nice. So that's the previous image. I'm just showing the connectivity matrix here. And the edge weight distribution. So you have a lot of edges that have a small occurrence, and only a few edges have a high number of occurrences. We found that for about 62 out of 75 patients we looked at, these markings correlated with where the MRI findings were the MRI findings were found for these patients. The ones that didn't work quite nice are the ones that are in these red circles here. And this was the main result of my PhD. I'm still working on publications here. But what I want to talk is there's these virtual cycles in computational neuroscience, which is we go for experiments, we acquire data, usually from people, patients, from various modalities, e.g., MRI, anything. Then we analyze the data, which is what I showed you so far, this type of connectivity analysis and other types of connectivities. But there's a missing link here, which I haven't introduced so far, and it's what I want to try and work with going into a postdoc. And is to create a computational model, put a computational model in the cycle. So fortunately, there's interesting computational model called the epileptor model. Basically, it's a model that can seize. It can create seizures. It can go from a type of mildly chaotic activity to a highly regular activity. And it's used to replicate the activity from cortical models. So it's this set of 5 differential equations. We can do a coupling. So we can create epileptor models for different brain areas and use this coupling in this slow variable here, which is this one, to make one component, one area change the dynamics from another area. Here you have a phase space, which is the animation that goes through here. So there's this vertical line here, which is this low variable, that is the permittivity or excitability from our network. And it rules if it goes in or out of this highly regular type of activity. The coupling, we can use physiological data from the structural connectivity from the connectome. So basically, the number of white matter tracks that connect different brain areas, we transform this into a matrix. And what we do is use this as a coupling for epileptor model that, for many epileptor models that are coupled to mimic something like an EEG signal for the whole brain. So this would be the source of our epileptor models, right? Here, the ones that are colored, they have a value of excitability that was set to replicate the seizure onset zone and the propagation zone in blue. They're separated by hemisphere, so you can see that even if the parameters don't change, this excitability parameter doesn't change for the other lines that are colored gray. The activity propagates because of the coupling, but it's not seen so much at the source level on the other hemisphere. And to transform this source signal into a signal that's more similar to the EEG, we go through this EEG gain matrix, which says how much of our EEG channels are composed by a linear combination of these sources. So here you're going to have the EEG electrodes, and here the brain areas that correspond to these weights. And in the end, you get something that looks very much like an EEG signal. This is artificial. Of course, you can make it to fit your EEG. You can change the parameters from the models to change your EEG data. This is on the virtual brain. And you can see that it goes through a transition that's quite similar to a seizure. It goes from this random-like activity to something that's very regular and very high intensity. And when we do connectivity analysis in this, well, you can guess where I place the sources with higher excitability. This is on the virtual signal. So yes, we put the higher excitability here in the left hemisphere, which is quite nice. It's just saying that our connectivity manager does relate to something we can model somehow, and just to see if our model works on a toy model, our connectivity works on a toy model, and it's quite nice. But what's even nicer is that this connectivity signature is strong even before the seizure starts. So on our toy model, not for actual patients, because if it was, that would be fantastic. But on the toy model, at least, here we have a section of the EEG that does not contain the seizure yet, but it does contain some high activity on the epileptic sources. And when we do a connectivity analysis of this signal, this EEG signal here, you can see there's heightened activity on the areas where we put the focus, because this is an artificial signal. And the idea, just to conclude, is, multi-synchronization can be used to try and localize the epileptic focus on scalp EEG. The connectivity patterns found, I didn't go into this too much, but maybe you can ask me about this later. And we can try and use multiple synchronization to make more accurate models, and also try and simulate the effects of stimulation. So here is multi-electrode transcranial brain stimulation, where you are injecting current into the brain instead of just measuring potentials. And the idea is to see if you can alter brain connectivity on the long term by introducing external activity. So that's all I wanted to say to you guys. I want to thank my advisor, each and every one of our collaborators, Professor José Garcia Miranda from UFPR, Professor Yu Jiang Wang from Newcastle University, Fernando Sendes, Bruno Campos, Marina Alvim, people from LASCON. I don't know if you guys ever participated in LASCON, but everyone who is in computational neuroscience should. I strongly advise you. It's an intense school. It's a whole month. I did this in the beginning of this year. I recommend you to go to whenever the next one happens. And that's all. Thank you very much.
Thanks, Leonardo, for this nice talk. We have time for questions. Okay.
Thank you for the talk. My question is, what's the difference between motif synchronization and Pearson correlation for this time-varying functional connectivity?
Yeah. So Pearson correlation, coherence, these techniques, they are limited in a way which you can't look at very short time windows. You need to assume your signals are somewhat non-stationary, or stationary, sorry, you're close to stationarity. So usually you look at epochs that are, let's say for EEG, considering the average sampling rate is about 250 hertz, you look at windows that are 6 seconds long. Because if you look at anything less than that, you can assure to have something close to stationarity on your signal. They're going to be very non-stationary, which doesn't make your prediction very strong. These type of techniques, and also there's transfer entropy, these symbolization techniques, they allow you to have temporal window that is as short as you can, arbitrarily short. And it's very useful because these spikes or interactive events, they're very short. They're not going to take a whole seconds, and they get diluted in the middle of the rest of the activity if you look for that. But if they're if you have very short localized time windows, you're going to have something like that, which is, you're going to have a very sparse time-varying graph, and you're only going to have interesting activity when you look for the spikes or these short transients. So that's one of the reasons to go nonlinear, I think. There are other reasons, but those go into complexity and entropy, which I have some slides, but I hid them from the rest of the presentation because it's going to be very long. But I can show you if you have the time.
More questions? Okay.
When you create this ordinal data, why do you choose 3? There is some reason, there is some mathematical.
Oh, because, I mean, if you're going to increase factorially, right? So 3, you have 6 patterns. If you have 4, you're going to have 24 patterns. If you have 5, you're going to have 120 patterns. 3 is just the minimum interesting one. Everything else is going to increase your computational cost. So for 3, you can iterate very fast. Okay. The computation cost is low. There are some other groups, like Professor Fernando Selingardi. They look at the varying lengths and varying steps between the points you choose.
And my second question is, when you talk about this model, you can fit the model to recreate the original signal for a patient, or?
Yes, this is called virtual brain twins. So
there is some difference. My question is, these parameters depends of the gender, age of.
They're gonna the parameters on the epileptor. No, they are parameters. They are flexible enough as to you can try and fit. Of course, you have to do some filtering of your data. It's not gonna be a close match, but it's going to be an approximation. It is a toy model, right? But they do this. They do virtual brain twins for patients with epilepsy. They measure the EEG signals, and then they fit the epileptor models. And what they do is they remove the areas they think are the epileptic focus and look at the brain activity after that. So it's a predictor of whether or not the surgery is going to work.
Okay, so let's thank the speaker again. We had our last talk of the day, so.
Thank you.
We will see again tomorrow at 9. I